Last time we spent our lecture talking about the issues of power dissipation. We understood which is the problem and why the power dissipation for the power device is so important. Further, we described the way to analytical model the power dissipation and the temperature increase on the junction of the devices, introducing the aspect of thermal resistance. That is, however, a static value, a static quantity. Further, we take into account the aspect that says that a power device working in switching condition is not working with the constant power applied to it, but with pulses, short pulses, that are so short to be smaller than the typical thermal time constant of the system. It was the case to introduce the concept of thermal capacitance with the related time constants. The concept of thermal impedance is more adequate to describe the behavior of the chip of the power devices and more closely describes which is the temperature increase of the junction for the device. The thermal resistance, the thermal impedance here shown for a typical case with the chip, metal plate and substrate heatsink shows a number of thermal constants, and these aspects are then summarized in the datasheets of the power devices, where you will find graphs that are similar or very similar to these, where as a function of the duration of the pulse and as a function of the duty cycle of the, if it is a repetitive pulse applied to the system, you can have an estimate of the thermal impedance from the junction to the case. As we can see, typical values are smaller or significantly smaller than the actual thermal resistance that we measure in steady state. This has an effect on the safe operating area of the devices that is smaller when we work in DC conditions and is increased when you work with pulses that are shorter and shorter and tend to the square SOA when the pulses are very short. We then introduced the concept of dynamic power dissipation, how to measure it, and in the case of resistive load, we gave an estimate of the maximum power dissipation during the transient. It is now the case to think of power losses in a case that is more related to what we see in real applications. In real applications, the power devices are typically, the load is typically of the inductive type. It's not a resistive load. This means that we cannot write a relation that is linear between voltage and current on the device. And it is also not true that, for example, in this case, this is the turn-on phase, while the voltage is decreasing, the current is increasing. In the inductive load case, these two waveforms are less related. The typical load, as we say, is inductive. Here, in this case, we have a BJT as a power device, but nothing changes if we have a MOSFET or an IGBT or another power device. The load is this inductance here. The current of the device is the IL current indicated with this arrow here. Another important element is the freewheeling diode. This is always present because, as we said, the inductance, if there is a current flowing through the inductance, it cannot be stopped instantaneously. And this means that you need a way, a path for the current. This looks very different from the only deeply studied example that we had for power device application. But if you think of a buck converter, a step-down converter, the situation is exactly that one. We have the switch. The load is the inductance, and in typical condition, this inductance is the current through this inductance is constant, more or less, and flows in one direction. Then you have the capacitance and a resistance, but this is not important for the device when it switches on and off. What this is a constant current. This is the input voltage, and here, just here, what you introduce is a diode, a premium diode. This situation for the device is very similar to this typical test circuit for the inductive load. We have the inductance and the freewheeling diode. For the analysis of the turn on and the turn off in this typical inductive load test circuit is done assuming that there is a constant current flowing through the inductance. This is the typical case. The circuit is working, there is a constant or quite high current flowing through the inductance. If this is not the case, we can easily charge the inductance in this element here by simply switching on the device. When I switch on the device, this voltage on the voltage on the collector or drain side of the device goes to 0. The entire supply voltage is on the inductor, and the current through the inductor increases linearly. Then we wait for enough long amount of time, and what is obtained is the current that we want to use for the test. This means that it's easy to charge this inductor, and we can assume that this inductor has been charged. Let us analyze the first transient, the turn on. This is a BJT, but as we say, any other device will do the same. Turn on condition. We can plot current and voltage for the device as a function of time. At the beginning of the transient, since we are turning on, the device is off. The voltage is the supply voltage. This is the voltage on the device. Let's say this is the voltage on the device. And the current is 0. The device is off. At a certain point, the device will turn on, the gate or the base will be at quite high voltage, a current will go through the base, this device starts to switch on. What should happen is that the current increases and the voltage decreases. The point is that the diode here, for a resistive load, we would see a current increasing and a voltage decreasing in the same time. For an inductive load, what happens is that the current through the device starts to increase. But the voltage here cannot decrease instantaneously. This is the turn on. Maybe it's the opposite. The point is that the current is flowing through the diode. The device is off. The current is flowing through the diode in this way. The current is in this direction, and this means that the device is on. We can neglect the voltage drop on the diode with respect to the supply voltage VCC, and we can say that VC is equal to VCC. The only way to reduce the voltage here is to turn off the device. If the device is on, the diode is on, this voltage is clamped to VCC, the voltage here. This means that while the BJT is turning on, its current increases, but the voltage remains to VCC. This is the IL value, for example. When the current through the diode, through the device, reaches IL, the current of the inductor, only at this point the diode is on, because the entire current IL is flowing here and there is no current flowing through the diode. Only at this point the diode is off, the voltage, the reverse voltage on the diode can be positive, and this voltage can decrease. This means that only at this point the current, the voltage on the device decreases, while the current is at its maximum. The difference with the resistive load is quite big, because for the resistive load we would have had a current increasing while the voltage is increasing. Here the current increases while the voltage is at its maximum, and only when the current is at its maximum, the voltage can increase. This increases the power dissipation, because the product between voltage and current is large. A similar analysis can be conducted for the turn off. In this case, it is the opposite. This is the current, this is IL. The device is on, the current is flowing through the device, and this is the voltage, this is VCC, and the voltage is very small, the on-state voltage drop. At a certain point, the device is switched off. The gate or base voltage is brought to 0. The final result should be current going to 0 and voltage going very high. What actually happens is that this starts turning off. The voltage here increases, but the current does not decrease. Why? Because the only way to decrease the current through the device is having some current flowing through the diode. And the diode can be on only if this voltage is higher than VCC. So always neglecting the voltage drop on the diode with respect to VCC, we can say when this voltage is equal to VCC. This means that during the first phase of the transient, the voltage increases and reaches VCC. And in this time period, the current is still at its maximum. Only now, the current, the diode goes in the forward bias condition, the current through the diode increases, and the current through the device decreases and goes to zero. Also in this case, the voltage increase happens with the maximum current through the device, and this will increase the power dissipation. Everything works if we assume that the inductive load, the inductance is quite big. And for example, when during this phase in which the current is flowing through the diode, actually this is slightly dissipating the energy on the inductor. And this means that during this phase, the entire current is slightly decreasing. But if VD is small, the voltage drop on the diode is small, and this inductor is quite big, it contains a lot of energy, the current decrease will be very, 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 very small. During the transient, you can assume that this in current IL is constant. For the simulation, sometimes instead of using the inductor, you can also use a current generator. Because in this condition, if the time constant of the inductor is very slow with respect to transient times, this can be this is the case. The current of the inductor is constant, it behaves like a current generator. This can be useful sometimes for the simulations because the current generation doesn't need to be charged. The charging phase is very slow, and this means a long simulation. With the current generator, you can start from the final state. These are tricks that are useful for for reducing simulation time or improving the convergence of the simulations. This is a visual comparison between the two kinds of switching. This is the resistive load, turn on and turn off, and this is the inductive load. It is clear that this kind of transient increases the power dissipation. But there is nothing that we can do. If the circuit is what we showed, the only way to reduce the voltage is having a maximum current. The only way to increase the current is having the maximum voltage. And this is the absolute. Actually, the situation is even worse because there can be ringings or overshoot on the current, for example, or on the voltages. And this can also worsen the situation. For this kind of switching, we can also plot the instantaneous power dissipation. And in this graph, we compare the instantaneous power dissipation for the two types of switching. The blue line is for the resistive load, and the red line is for the inductive load. In this case, the switching time is assumed to be 200 nanoseconds. The load current is 10 amps, and the maximum voltage is 10 volts. For the inductive load, the maximum power dissipation is the Imax multiplied by Vmax, and is 100 watts. For the resistive load is 1/4, is 25. In the end, the average power dissipation, the energy that is dissipated in the two cases, is more than 3 times larger for the inductive load. It is also interesting to analyze the path of the operating point for the device in the current voltage plane. This is the turn on. We will start the transient here with the maximum voltage applied to the device and the zero current. During the first phase of the transient, the voltage remains constant and the current increases. We are moving vertically through the plane. When the current reaches its maximum, and we are at the maximum point of maximum power dissipation, here the current remains constant and the voltage decreases. We are moving with this square path on the plane. For a resistive load, we would have moved like this, or with a straight line between Vmax and Imax points. Usually this power dissipation is not very high for the circuits, for typical power devices, and this means that there should be no safe operating area problems due just to the switching, but also the pulse should be taken into account. Obviously, the Vmax value and Imax value must be in the safe operating area. Otherwise, you have other kinds of problems, not the power dissipation. There are also, we will see those later, other parasitic effects that have not been introduced in our analysis that change the shape of this path. For example, if we introduce the parasitics, probably the path would be like this. We'll jump above Imax, and then we'll go to Imax, and in the other direction we'll jump above Vmax, and we'll go in this direction. It is important that during the switching you do not overcome the safe operating limit, otherwise the device is destroyed for various effects.